Nice.
Okay, we are on parent functions, and we're looking at the cube root. And your parent function for this is y equals the cube root of x. When you write it as a rational exponent, it could also be written as x to the 1/3. Okay, these are identical. This is called rational form. This is called rational form. This is called radical form, right? Let's just take a look at it. You've got a little bit of a graph over there. Kind of curves up this way, kind of curves that way. I know it's not a perfect graph, but that's what we're getting. What is my domain on this baby?
X is an element of the reals.
X is an element of the reals. All real numbers. It can be any number. When you look at domain, you look left to right. I could plug in any number whatsoever. My range is when I look up and down and I say, okay, what can Y be?
Y is an element
Anything.
of the reals.
Y is an element of the reals. Even though we only have a short picture of the graph, if we took it out forever and ever, it would keep growing up this way and down this way. Alrighty. What is my y-intercept on this one?
0, 0.
0, 0. And my x-intercept?
0, 0.
Same thing. Okay? Symmetry. This is considered to be symmetric about the origin. Okay? Symmetric about the origin. Where it says asymptotes, your answer is none. There are no asymptotes. Okay? And I might get set up for doing the intervals of increase, decrease. So let's just take a look here. So you basically got action happening at 0, right? Okay. So what is happening from way over here till I get to 0? What is the graph doing?
Increasing.
It's increasing. What's happening as I'm going from 0 and keep going? It's still increasing. Now, you can see the curve is different though, right? Can you see how it's kind of curving up and under here, and then it's kind of out and over there? So when we talk about the intervals of increase, we want to use 0 as that important thing. So we're going to have two intervals of increase. One is going to be from negative infinity to 0, and the other is going to be from 0 to infinity. The reason you don't say from negative infinity all the way to infinity is because your graph doesn't increase the same way.
Yeah, it's not a line.
Do you see what I'm saying? Correct. It's not a line. It's not got the same thing going on the whole time. Alrighty. Intervals of decrease, that would be a big bunch of none because it's not decreasing anywhere. Relative local max, none. There's not any maximum. Relative local min, there's not any minimums. So none. Okay, let's talk concavity for a second. So here's my 0, here's my negative infinity. If you look at this first part, okay? Did I hope I'm looking at the right thing here. Okay. If you look at this one, this is actually concave up on this side, and this is actually a concave down on that side. Okay? And so where it says concave upwards, we're just going to call it cup. That's going to be from negative infinity up to 0. Okay? Concave down, cud. I don't even know how to do that. It's going to be from 0 to positive infinity. I'm trying to make up some good stuff, but it's not working for me.
I think it's going pretty well, actually.
So concave up, cup, holds water. All right.
Concave down, cud. Eats its cud. It comes out. I don't know.
It comes down.
Yeah.
I don't know. I don't know.
It's like a cow.
Cud.
Horseshoe.
Horseshoe. It does look like a horseshoe. Is that good luck? Which one's good luck? A horseshoe up or a horseshoe down? No, a rabbit foot is not good luck. Especially rabbit foot sitting in our yard. There's just like a dead rabbit foot there. I said, Randy, you think that rabbit foot's lucky? He said, not for that rabbit. Okay. Point of inflection. See, now they're going to want to watch all these just because of that little doodad in between there. Point of inflection is whenever you change concavity, okay? And we did change concavity right here at this little point, which is
0, 0.
0, 0. That is incredibly important, okay? Being able to find a point of inflection, I have a program that I need to give you for your calculators.
Okay.
If it's on mine today, I'll give it to you now. If not, I'll give it to you next week. But given a curve, no matter what kind, it's kind of like finding max min. You do like a left bound and a right bound, and it's going to go in there and find exactly where the point is at where your concavity changes.
Okay.
And that's a big deal. Okay. Later on, you'll work out mathematical ways to get it, but it's nice to have a little.
I think I have the cord for that too downstairs.
Okay. Well, I'll look on there a little bit. Just remind me. Okay. Let's see. In behavior. As x approaches negative infinity, what's y doing as we go this way?
Negative infinity.
Okay, y approaches negative infinity. And mine always look like crazy 8s. Okay, as x approaches positive infinity, what's y approaching?
Positive infinity.
It's approaching positive infinity. Alternate forms of the equation, it's going to look very similar to our square root business. It's going to be y equals a cube root x. The minus h goes under the radical there, and plus k is on the outside. Again, the h moves it left and right. The k moves it up or down. Correct. Your locator points, which is just right under the graph there, on the parent function, it's 0, 0.
And hk.
And hk for your alternative form. All right? So that's going to do us for that one.